Epilepsy is a chronic neurological disorder affecting over 50 million people worldwide, and timely diagnosis is crucial for effective treatment. However, current EEG-based seizure detections rely on centralized machine learning or deep learning, which requires pulling sensitive patient data into a single repository. This approach raises a serious privacy concern, as data breaches could expose highly confidential medical records. Our work addressed this critical challenge by leveraging federated learning, a decentralized framework where models are trained locally on distributed devices, such as hospital or personal variables, and all model updates, not the raw data, are shared. This ensures privacy while enabling collaborative learning. However, existing federated learning models for EEG analysis often struggle with accuracy and efficiency. To bridge this gap, we introduced NeuroFed-TCN, a novel temporal convolutional network optimized for federated learning. It is designed to capture long-term dependencies in EEG signals while preserving data privacy. Let me explain why this matters. Current seizure detection system face three major limitations. First, centralized storage of EEG data makes system vulnerable to breaches. Second, EEG patterns vary dramatically across patients, making generalizations difficult. Third, most models struggle to capture the long-term temporal dependencies crucial for seizure identification. NeuroFed-TCN solved these problems through a privacy-preserving federated framework where models train locally on hospital or personal devices and only share updates, never the raw data, to the centralized model. Our TCN architecture specifically handles EEG sequential nature through dilated causal convolutions and residual connections, outperforming the traditional CNN and also RNN. Here is how we implemented it. We used the UCI epileptic seizure dataset containing 11,500 EEG samples. After balancing the data with Jian method, we distributed it across 20 simulated clients. Each client trained a local NeuroFed-TCN model using either FedAvg or FedDyn aggregation. The TCN's design is particularly innovative. Its dilated convolutions capture multi-scale temporal patterns while causal convolutions prevent data leakage, making it ideal for real-time detection. Residual connections enable deeper networks without the vanishing gradient problem common in RNN. The results were remarkable. NeuroFed-TCN with FedAvg achieved 96.98% accuracy, 97.68% of recall rate, and 96.25% of specificity. This outperformed all the benchmark federated learning models and even the centralized approach like DNN. It converged faster than other models, reaching optimal performance in just 4 rounds, while FedDyn showed promise for handling data heterogeneity. FedAvg proved more efficient in overall. More importantly, our model maintained this high performance with only 9.7 million parameters, making it practical for deployment on edge devices. In conclusion, NeuroFed-TCN represents a significant advance in privacy-preserving medical AI. By combining federated learning security advantages with TCN temporal modeling capabilities, we have created a system that matches centralized models' accuracy while protecting the sensitive patient data. Future work, including clinical trials with hospital partners and optimizations for wearable devices, are needed. This research demonstrates how we can harness distributed data to improve healthcare without compromising privacy, which is a crucial step toward the ethical AI in medicine. That's all for my presentation. Thank you.